Um, Hello everyone. Yeah, I'm so glad you all being here today, join us in person and online. So today I will share our research, talking about the mortality inequality across U.S. both in state level and county level data. So this is a teamwork. My co-authors include Yuan, Megan, Guozhen, and Zhijia. So I really enjoy working with you. Thank you all. Sorry. Can Okay. So firstly, let's give a brief review about what we knew about the mortality differences across US. Here we show the range of mortality across states in the United States from 1969 to 2019 for females and males. Here we can apparently see we have a divergence in not, especially for the females. So when we measure the mortality disparities with the standard deviation of age at death, both at the per capita death rate, the disparity persisted in those two measures. So this is consistent with published studies previously. So demographers also talked about the mortality rates and their relationship with the population racial composition. And they have also found about the mortality disparities according to the income distribution within the US by county level data. So all of these studies are always talking about the summary indicators. But all we know that mortality rates varies at different age groups. So these age patterns could change over time and vary across different places. So here we want to say, what about the fact of the geographic mortality inequality beyond E0 or variance of age at death from age 0 at both the between state level and within state level. So to answer those questions, we did several steps. Firstly, we take the whole US as a reference population and compared each state with the US to assess the mortality gaps measured by E0, variance, and crude death rate. And then we use the novel decomposition methods to assess the age-specific contributions to those mortality gaps. I will talk the details about the methods later. And we also compared the between state and within state variation of life expectancy. Thirdly, we also talked about the impact of racial composition and income gradients on mortality variation across states and within states. Here, I want to clarify that when we're using the word variance, we are specifically talking about the lifespan inequality measured by the variance of age at death. And when we use the word variation, it's like a general variability. So our data life table statistics by state level and county level comes from the United States mortality database, and the racial data, population racial data and income data comes from census and American community survey. Here we want to say thank you, Magli. Thank you for sharing data with us and inspired us to explore the mortality by state level and county level, and also give us some valuable suggestions at the early stage of our research. So I have about 6 main sections of our findings. Firstly, let's go through the E0 this aspect. In general, we use μx to express the mortality rate. So from the observed data, we can easily calculate the proportional differences between two populations. Here we show the proportional differences in mu-X between California and the US. The blue line shows the situation in 2019. So we can see almost every age group, California's mortality rate is lower than the US. And based on the mortality rate, we can calculate the E0 for the US. And using the Caffey's entropy approach, we can get the sensitivity of E0 to the proportional change in mortality. So here, figure B shows it. It shows what will happen to E0 when mortality decreases at different age. So here, the infant age and old age is the most important part. And then we want to compare the E0 between California and the US. Since we have already know what will happen to the E0 according to the sensitivity, and we also know the proportional differences in mu-X based on the observed data. So we combined the two parts, we can get the age-specific contribution to E0 gaps between the two populations. Here, the point I want to mention is that only if one age group have the significant or large proportional differences in mortality rate and both the large sensitivity, that age group could contribute large to the E0 gaps. For example, let's see about age 20, the differences in mu-X is large, but the sensitivity is almost zero. So the contribution is always near to zero.
Are you doing this for both sexes pulled together? Sorry? Are you doing this for both sexes pulled together?
Yeah. So here I just showed an example for female. Yeah.
They're not pulled together. Here's a mold.
So does our methods work? Is the decomposition accurate? So don't worry, we did the check. Here, we sum up the age-specific contribution to the E0 gap, that's the total E0 change, and add this value to the baseline US females E0. Then we will get the new E0 value. That value we call the estimated value of E0 in California. And in figure D, we compared those two values. We can see it performed perfectly.
So, can you understand what's the estimated E0?
So we use this method. We can get the age-specific change of to the E0 gaps, right?
Okay.
If the estimated is lower than you observed, and the contribution of California are positive, California has lower mortality than the.
So the point here is that we use the estimation, this thing, to calculate delta E0, estimate delta E0. Then we add the delta E0 to the US number, and then we come up with a number. That's our prediction for California. And then we compare it with the actual in California.
Okay.
And if the two are close, then we're good. And if they're not, then
And what we're seeing is that they're close for the last, whatever, 10 years. And so probably they're close all the way back to 1970.
no, it's all the way from 1970 to 20.
Oh, it is.
Just overlaps.
I see. It just is so close, it doesn't even show.
Which surprised me.
Okay. So we apply this analysis to all of the 50 states. Firstly, let's see the examples from California and Texas. Here, the E0 in California is higher than the US average, and Texas is lower. So we broke those gaps into age-specific contribution. We show three wide age groups. Here in California, the youngest age group contributes least, and the middle, as well as the oldest, contribute equally. But in Texas, the case for the youngest age group is the same. But when we see the old age group, the contribution is over 100, and for the middle age group, it has a negative number. So here, since we have 50 states, 50 years, and 2 month figures, so we just want to figure out which age group plays the most important role in the ENOT gaps. So here, we just take the absolute value from the contribution and divide it into 3 levels to show, we say the slight, moderate, and strongest contribution to the ENOT gap. So in this table, we can easily see the oldest age group makes the most important contribution to the Texas lower ENOT than the US as an average. So in this map, I just show the magnitude of contribution by age group to ENOT gaps between each state and the US in 1969 for female, male, and 3 age groups here. So apparently we can see that many states in the youngest age group have the slight color. So we can say the youngest age group contributed least in most of the cases, and the ENOT gap mainly comes from the middle age and the old age groups. And when we see the males, the middle age group contribute even more than the oldest age group. And when we look at the change, this map is for the 2019, and both for female, male, and 3 age groups. Here we can see that the youngest age group, even the contribution from that age group was even less than before. And the contribution for the middle age and the oldest age group has gradually increased. Then the next part, we used the same strategy to analyze the variance of age at death. Like what we did before, we just show the proportional differences in mu-x and the sensitivity of variance of age at death. And these are age-specific contribution to the variance gaps. Here, the point I want to mention is that the threshold age. So death occurring before the threshold age would decreasing the mortality inequality. And death occurring after the threshold age would increase the lifespan inequality measured by variance of age at death. Since we have found that the youngest age group contribute least for the mortality variance, so here we just talk about the variance of age at death for people who are alive at age 6 and after. So we use the percentage differences to assess the variance of age at death gaps between states and the US. Here the example is also California. So we got the percentage differences in variance of age at death, and they're broken down into 2 parts. The first part comes from the contribution of death younger than the threshold age. That part would decrease the lifespan inequality. And the second part is contributed by the death older than the threshold age. So we did the analyze to all of the 50 states. The brief summary here is that deaths of differences of deaths occurring before threshold age was the main contributor to the state level mortality inequality. And when we look at the specific cases, such as southeastern states, such as Mississippi, the lifespan inequality is considerable, and it has even increased over time. For the third part, we will talk about the number of per capita death rates. Here we use the Kitagawa decomposition approach. Like you can see, the first equation, Cx here, is the proportion of individual age X relative to the total population. So from this approach, we can broke down the true death rate between states and US into 2 parts. First part, like shown in the green color, is contribution differences from the mortality rate of the two population. And the second part comes from the differences in age structure of the two population. Here's the example in California 2019 females. We can see a contribution from the mortality rate is about 65%, is about 2 times of the differences from age structure. So, but what about the contribution? Which factor contributes more in other states? So we draw a map. Here, I use 2 colors to show the types. The red color means in that state, when we compare the crude death rate between that state and the US, that gap is mainly contributed from the differences in age structure. So obviously, California is a green color. That means differences is mainly comes from the age-specific mortality rates. So we counted the number in 2019 for females, we have 26 states with a different major contributor is the age structure. And for males, it have 23 states. And we calculated the number of states for over the 50 years from 1969 to 2019. So here, the red color is consistent with before. It shows the number of states where age structure contributes more. So here we can see every year for females, age structure contributes more than the age-specific mortality rate. And for males, even though after around 2,000 years, the two numbers of states is equivalent, but we still have half of the states where age structure matters more. That means when we talk about the crude death rate or the death numbers in each state, we cannot ignore the age structures. And when we look back the equation here, we can also break down the gaps or the contributions into age group. 2 factors, 3 age groups. Those numbers sum up is 100%. So like we did before, we also divided the contribution into 3 levels to show the importance of different age groups. Here shows the example in 2019 for females, the contribution from age structure, mortality, and 3 age groups. Here we can see almost every state for the youngest age group has the lowest contribution. So at both the age structure level and the mortality level. So when we look at the oldest age group, obviously from the E0 findings, the old age groups do matters. But when we look at the age structure differences above age 65, which we can also say population aging, that makes the most important contribution to the crude death rate gaps. So, and this contribution has increased over time. We just show the end of the time maps here to show the example. For the third part, we compare the between state and within state variation of life expectancy. Firstly, let's see the E0. Here, for the picture, x-axis for the E0 values. The y-axis is a state. So each blue bar represents one state. And the right end of the bar means the maximum E0 within that state by county. So the left end is the minimum of E0. So the length of the bar means the range of E0 within that state. Here, the largest range is about 9 years in South Dakota. And we also we use this to show the within state variation of E0. And we also show the between state level variation, use the red color. So the red color, the right and the highest E naught or the maximum E naught by states and the lowest one. And this black point is the national E naught. So we use this to measure the between state level E naught variation. This plot is for female in 1990, and we also did the same plot for 2010 to show the change. So here we want to say the range of E naught across counties within states. The highest number was higher than the range of the between states, and the variation of this range was increased over time. We did the same thing to check the E65, so the findings is consistent with E naught. Now, next part, we will talk about the impact from racial composition here. In this figure, the x-axis, we use the percentage of Black people to show the racial composition, and the y-axis is the gaps, mortality gaps between each state and the US. We show the gaps in E naught, true death rate, and variance of HIV death, both for females and males. So for the point, a series of points with the same color show one state over the 50 years. So we can look at the green area of each plot. That means states where percentage of Black people over 20%, they always have lower E naught, higher crude death rate, and higher lifespan inequality compared to the US as an average. So in this case, racial composition could explain something about the mortality variation across states. But when we look at those states or cases where percentage is lower than 20%, it's not good enough to show a good pattern. So they must have other things matters. Our conclusion here is that racial composition is not good enough to be a solo predictor to explain the geographic mortality inequality across states. And the last section is about income inequality. Here, we use the data by county level. For example, here shows the counties within California, and we ranked there. For each county, we have their median household income and their E naught. So we use a percentile to show the income distribution across the counties, and the y-axis is E naught. The relationship here shows that counties with higher income generally have higher E naught, and this relationship or this slope increased between 1990 to 2010. So we say that they have a greater disparity in E naught by income distribution. So here we use the ratio of slope to measure the change of this kind of disparity, and map again. Here we also use different color to show the change patterns of this mortality disparity. The red color means just such as California we show here, the mortality disparity has large increased. And for the white color, we show states where we didn't see any obvious change for the disparity. And the green color means the disparity has decreased. So here the conclusion is that mortality gradients by income inequality within states has increased in many states, like shown in red color. And we also check this pattern for E65 is consistent with before. And the case for standard deviation, for the county level data, we just have have the 5 age groups. So we just use the standard deviation from age 10. And this is has a negative relationship. That means counties with higher income they always have the lower lifespan inequality, the better performance. So, but the pattern for the map, we also use the consistent color with before. The conclusion here is also consistent with what we found in E0 and E65. So this kind of mortality variation gradient by income inequality distribution has increased in many places.
Do you want to talk about this substantively at all, or do you want to keep going? Is it okay to ask a question?
It would be better if we do that later. Thank you. So let's do a brief summary about our findings here. Firstly, the improvement in infant mortality has equally benefit in all of the states across US. And the mortality inequality, especially as the middle and old age groups, has significant effect to the mortality variation, and in some cases has even increased. And when we talk about the within state differences and the between state differences, the within state differences are significantly more larger or considerable than the between state differences. And here for the population racial composition is not a really useful way to talk about the source of mortality inequality geographically. And finally, the within state mortality varies with income, both the mean or the variance of age at death. And this kind of inequality has in many cases increased over time. Okay, the final part is our conclusion about our contribution. Here, for the measures part, we use the normal measures to decompose the differences in aggregate measures into contributions from the age-specific rate and both the sensitivity of that measure to the age-specific rate proportional changes. So this approach can be applied to other fields such as fertility or migration if we can figure out the sensitivity of those aggregate measures. And the second part is about the implication here. So we want to say geographic mortality inequality for specific age groups has increased over time across the US, and we suggest that policymakers should focus on the local differences within states between counties to reduce the mortality inequality, and lastly, addressing the causes of significant between state and within state mortality inequalities should be helpful to increase the lifespan in the whole United States. So that's the end. Thank you all. Looking forward for comments, questions, suggestions.
Okay, please go to slide 25. Oh, sorry. Okay, so 26 then. Yeah, so I was trying to think about a story that summarizes why the shift in gradient is different for men and women. So Minnesota, Iowa, Illinois, Texas. So what's happening? So it's trying to think, is that what people are dying from? Or is it that people, anyway, this seems really striking, that places are becoming more equal for the deaths of women by income and less equal, the same places and less equal for men.
It's a really good, interesting question. Actually, we just did the descriptive findings just now for from nowadays. For our future, maybe we will talk about the reasons why these kinds of patterns show. And maybe one reason is that we should check about the significance of the slope. And the E0 of females is always higher than the males. So maybe that's what
Yeah.
we will check.
Well, the story that we thought of was that maybe income really matters in the last few years of life. I mean, there's a lot of studies in the past that have said this. And if you look at the HRS, for example, people have analyzed, you look at age of death, and then you look back and see how much those people, in terms of wealth, whatever they had, and you see a gradient in the last few years of life. And maybe that's why you see it in females, that they live long enough for these differences to matter. It's just a story. I don't know how you could test that.
Continuing on this theme, I'm not sure how this works out, but it's a kind of standard finding. Well, first of all, how is income measured when you're talking about income inequality? Is this individual or household or couple or?
Individual. The median household income we use here.
Household income, okay. So in earlier times, female labor force participation was lower and so on, then household income would be a better reflection of male education than female education. And it's often the case in many studies that the income differences found for females are much smaller than for males. But it may be that between 1990 and 2010, although I'm not sure this is factually correct, the female labor force, female earnings rose enough relative to males and so on that household income maybe is a better income for both males and females, and that might explain an increase in that gradient.
Yeah, well, first, thank you for your work. It's always very exciting to see that all the efforts and the time we spend on, assembling data and constructing the life tables are useful to other people, and I want to recognize Celeste's major role in developing this data. I have a number of questions, but following up on the discussion here, so these differences between men and women could be due to the fact that the mechanism explaining the interactions between income and mortality are not the same for men and women, and the weight of these mechanisms have changed over time differentially. And so maybe what is important for women evolved positively, and for men negatively, I don't know. But it's true that there are interactions between income and education as well, who impact on mortality. And I was surprised that you treat separately like race and income, and you don't try to look at this all together. So you look at race, income, and education all together, maybe sex, because the interactions are going to be different, and that will give you more information. I mean, there is also strong interactions between income and overlap between income and education. But why did you choose to do it separately instead of putting everything together and look at the?
Actually, I tried to put everything into the hierarchical model to show the regression relationship, but maybe I don't know why they didn't show a really good result. So here this step we just show the separately findings. Maybe we'll work it out what happened in the actions. Thank you.
Once again, thank you for this talk, and it's really exciting to see the USMTB data used. So one of the differences between the state level estimates that we produce and the county level estimates we produce, the state level, we produce our life tables through direct estimation methods. County, we use Bayesian inference to produce the life tables. And so the life table indicators that we publish for the counties, not only do we have a median, but we have confidence intervals around all of those points. And those are that's extremely meaningful, because especially for our smaller population units, those confidence intervals are quite large. And I'm wondering if you're using those confidence intervals, for example, in the graph that you show here in the upper right, are you using those weights to in your analysis? Because some of those, there's for example, there's a crude correlation between smaller population county, probably be more rural, probably having lower life expectancy. And so a lot of those lower life expectancy points are going to have a larger confidence interval.
Okay, thank you for pointing out the important information. Maybe we will check the confidence level later. It's here we just show the.
Yeah, I mean, it gives a good snapshot. Yeah, for sure. It's really meaningful.
Thank you.
Okay, if there are no more questions from I won't ask all of them, we can talk about it, but one of the questions was why did you use that time period? What's significant about this time period? Because the data for the county is available since 1982 and for the states since 1941 in the database. So why not look at the whole time period? And the second one is about the fact that some of the states are 3 counties and some of the states are like 200 counties. And you'd expect probably more variations. It depends on other factors too, but there are some states where you would expect more variations because you're looking at smaller units and many more units than in states where you only have 3 counties. So how could you take that into account? And same thing about you're saying that there are more variations within state than across states. But again, you have 50 states, but you have 3,000 counties. So you would expect more variation within states, if only because there are so many more units of analysis and you're going down and there is more homogeneity in what you're looking at. So how could you take that into account to interpret the results?
Okay, thank you for the question. Firstly, here we just take 1990 to 2010 because we use the median household income from the American Community Survey every 10 years. So maybe we can consider about change the measure of the per capita income that has a single year data. So that may be consistent with what we did before. And second, actually, I can show you another picture. Sorry. Okay, here. Actually, this picture shows the x-axis is an E0, y is the range of E0 of each state, and the size of the point is the number of counties per state. So here maybe we also checked about the question you mentioned about the some states have 150 states and other states has just 3 counties. So here didn't show a really good pattern about the numbers of counties within that state.
Well, you can see that all the small counties are in the low range. Like the blue dots, 0 to 20, they're all below. I mean, you want to see, but they're all at the bottom of the.
No, they're not. I mean, if you look at the lower left-hand corner, there's a whole bunch at the top.
Well, 20 to 40, but the small ones. Anyway.
I mean,
I think it's important to.
I agree, but I couldn't see. We all look at, and there's no consistent pattern that we could.
Some of those states with the smallest number of counties happen to be like in the North Atlantic seaboard where outcomes are really good, and then it's like in the Southeast where not only are there like the structural issues like race and income and all that, but administratively those states are divided into hundreds of tiny little counties. So there's these different effects that are coming.
Yeah, the size of maybe it's the size of the county as well, rather than the number. Like if you have 3 gigantic counties. I mean, Shasta County in California is huge, but the population is small compared to Santa Clara County. So I don't really know how to incorporate that. But any ideas would be more than welcome. We did look at different things. You didn't see balance.
Are there other? No. Not? Did you have a question?
No, Shaw does online. Yeah. So Ron Shajing.
Here maybe.
Yeah.
Racial concession. Racial segregation would be better. especially for explaining the geographic heterogeneity in life inequality.
I can say a little bit about that only in the sense that it's not clear what a good measure is of racial segregation. So one approach to this is to look at constructing segregation measures based on neighborhoods that people live in. And Yuan is at Stanford, and he's tried to do that. He's tried to create a sort of a segregation map in the United States. And maybe that kind of thing might be useful here. The difficulty for us was just having a simple measure of segregation that we could look at and say, this is why it's different from else.
It may also be more relevant in states that have larger Black population. I think there are big parts of the US where there's a very, very small Black population in a lot of the counties. Right? I just moved here from Wisconsin. There are many, many counties where there are almost no Black people at all. So that makes sense. If you're trying to look at within state variability, that's probably relevant for parts of the country and not for other parts.
Yeah.
So I have a couple of minor points. One is, so there was a National Academy of Sciences report, a wonderful report, it was probably 2012 or something, but it was trying to understand why life expectancy in the US was lower than in other high-income countries. There was a chapter in there by John Wilmoth on income inequality, and I think he was using county data. And, okay. And I think the conclusion was it didn't contribute very much.
A third of the, so again, the goal of the work was to look at how much heterogeneity within the US, so geographic differences in mortality within the US explain the gap in life expectancy between the US and other countries, with the idea that maybe actually what's happening is that the worst of counties or states are dragging down the US, but the counties or states that are doing well are actually doing well compared to countries. And what we found is that about a third of the gap between the US and other countries explain a difference in life expectancy at birth for male and only a quarter for female. So it contributed significantly, but it wasn't the main. And I actually found, I published something recently on socioeconomic inequalities rather than geographic inequalities. And I showed that even if you divide the US in 10 groups from worst, so socioeconomic is a combination of education, income, and a bunch of other variables. And even if you look at the best of the 10% Americans, the best of counties, they're hardly doing as well as the average OECD population. So even people who are living in nice areas have poor health outcomes, much more than
Now, as I recall, there were at least a few studies of mortality differences using at the county level, using socioeconomic status, maybe in the mid-teens, 2015 or something. I can't quite remember, but anyway, there's some things you can compare to and maybe say we're doing is right. But the sort of small and just technical point, I think substantively you're absolutely right that reducing income inequality would raise US life expectancy, but in a journal article or something, you'd have to be careful how you put that, because you can reduce inequality by lowering life expectancy at the top. if you imagine there's a fixed amount of resources and you're reallocating them from the top to the bottom, then it will raise the mean if the bottom is more responsive to the resources, which it almost certainly would be. And, you know, just things like that.
Well, but because we know from the research that one of the reasons why there are obese inequalities is heavily driven, like you showed, by working age adults.
By what?
Working age adults,
Yeah.
between 20 and 65, let's say. And we know that saving a person who is 20 will add more to national life expectancy than saving someone who is 65. Then we know that investing resources in the poorest areas or poorest individuals will have more of an impact than wealthy people, right?
It's just that we were surprised when we looked at the old age contributions to things, like, you know, we thought they'd be small. In fact, they're huge.
Yeah.
It's just consistent with the kind of thing we were talking about 10 years ago. Old ages are becoming more important.
I have another question, which is the trend, so the fact that there is increased inequalities across states and counties over time. How much do you think this is due to selective migration?
No,
Well, just in general.
it's just, you
General
know,
question.
changing slope.
Oh,
The fact that you found, not in relation to income, but in general, you found increase in inequalities over time.
Yeah.
Right? How much do you think this is driven by the fact that there is selective migration? So there is a redistribution of the population over that period, with basically a sorting out based on probably income and race and other things like that, but inclusive health status. So that people who are healthier are moving from poor counties to wealthy counties, or from high mortality counties to low mortality counties, and people who are unhealthy are moving from high mortality counties to low mortality counties, and so it's more transmission.
I mean, the only thing we have that sort of relates vaguely to that is the finding that age structure matters in a lot of places, which would tie into the migration story, but mortality rates matter in a lot of other places too. So, you know, we couldn't find a clear pattern that said that, you know, there was a trend. This, and so maybe the structure mattered more, which would be consistent with the migration story. But I don't. That's
Thank you. Thank you once again. That's super interesting. So at the very beginning, the compositions were showing, you showed like predicted